Hi everyone, welcome to CHEM. Now today's video is our molecular orbital theory part 3 video, and here we are going to deal with MO energy level diagram of oxygen molecule. Helium-2 in excited state exists, and brief idea about the molecular orbitals of lithium molecule to nitrogen molecule, and we will deal with diagrammatic representation of term interaction. So let us start. Now before starting, already 2 videos are uploaded in channel. You can watch it. I will give the link in the description box as well as the I button present above this video. And if you are new to CHEM, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us see. So first we are going to deal with molecular orbital energy level diagram of oxygen molecule. So in this case what will happen is that we have 1s orbital. So 1s orbital will combine in phase or out of phase to form a sigma bond. Similarly, 2s orbital will combine in positive and negative phases to get sigma and sigma star 2s, and next we have 2pz. This 2pz will combine in phase and out of phase to form sigma 2pz, and the other two, that is 2px and 2py, will form pi bonds. When they combine in phase, they will form pi, and when they combine out of phase, they will form pi star. So let us see how to do it. So this is the combinations present. If we start with 2s, so how should be the wave functions? We have, this is 2s, we can write it as sigma bond formation due to this 2s's like this. Positive for this phase, this is positive, this is positive. We have positive in both sides and a general electron cloud around this. So this is our sigma b for 2s. Now if we try to draw for out of phase combination, so we have positive and we have another negative out of phase combination. So this will form like this. We will have a nodal plane in between, and here is the formation of 2 places. This is positive and negative. This is already being discussed in the organic chemistry videos, and you can watch it. I will give the link in the description box as well as the I button present above this video. So if you want to know it in details, you can see there. Now we will see the combination of 2pz's. So 2pz looks like this, right? But we should not draw it like this. Proper way of drawing it is, we have one node in between. So these looks like 2 lobes detached. So one will have negative, one will have positive. Similarly, we are doing in phase combination. So this will have positive, another will have negative. This we are seeing for 2pz. Now this will combine to form a toffee like structure. This will be a bigger one and this will be like this. So this will be our negative, this will be our positive, and this will be our negative. So this is sigma b 2pz. Now if we try to draw for out of phase combination, what will happen? This is negative, this is positive, this will combine with negative and positive 2pz to form this. One nodal plane will come in between. This will be a bigger lobe, another side's positive will become short, here's negative will become short, and this positive will become long. So we get it as sigma star 2pz. Now if we try to look into our pi bond formation, so what will happen? See here, we have this as 2px, so positive, negative. Similarly, we have positive and negative. So this is our 2px. Now we combine this in phase combination, so we will get a nodal plane in between, and here is the 2 points. So here we will get like this. and this will be our positive side and this will be our negative side. And last but not the least, when this combines out of phase, so this side will be negative, this side will be positive at the downside, so we will get it like this. See here, we have a nodal plane in between also, and the four sides will contain four charges. That is, this one will be positive, this one will be negative. Here we have a lobe, similarly here negative, and this side will be positive. So this is our pi 2px star, and this is pi 2px. Now we will see that how can we draw this in an energy level diagram. So let us start. Draw the energy axis. As you draw the energy axis, you have to consider only the valence electrons, valence shell electrons. So in case of oxygen, we will consider only 2s and 2p. So first of all, we will consider 2s. So here is our 2s, here is another 2s. So this will combine like this to form the two bonding and anti-bonding molecular orbitals. So one is sigma 2s, another is sigma star 2s. Next we will see for 2p. So 2p, there is 3 orbitals, and this will combine in phase to form sigma 2pz and the 2 pi's, which are pi 2px equals to pi 2py. Now this will combine out of phase to form pi star 2px equals pi star 2py, and lastly it will form the sigma star 2pz. So finally this is 2p, this is 2p, and these combines to give 4 pi orbitals, pi molecular orbitals, and 2 sigma molecular orbitals. Now we will fill up the electrons. So if you consider electrons, then 2s has 2 electrons for single oxygen, right? So here are 2 electrons. Similarly, 2p has 4 electrons. So 1, 2, 3, 4. 1, 2, 3, 4. Now we will put it in the MO. So for this 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7 and 8. So from here only we can say that there is some kind of paramagnetism, because there is 2 unpaired electrons present within. As you can see, there are 2 unpaired electrons here. So O2 is actually paramagnetic in nature. And if anybody asks you to draw or calculate the bond order, then you can easily do it. Number of bonding electrons minus number of antibonding electrons divided by 2, right? So what will be its bond order? If you see, here we can see that for bonding it is 8 and for antibonding it is 4. So ultimately it becomes 8 minus 4 divided by 2, there is 2, and we know that oxygen forms a double bond in between themselves. So thus we can conclude that it has a bond order of 2. Now if we want to deal with different kinds of stability of oxygen's ions, then we can try out for O2 plus, next comes O2 minus and O2 2 plus. So your work will be to find out the stability order of O2 plus, O2, O2 minus and O2 2 minus by giving up electrons or by taking in electrons. Find out the bond order, then you can easily find out the stability order. So with increase in bond order, the stability also increases. And remember to find out the molecular energy level diagram for F2, because after oxygen fluorine comes, right? Now we will deal with the existence of the excited helium-2. Now we know that what happens in excitation? We have in helium 1s and 1s, right? That combines to form our sigma 1s and sigma star 1s, right? Again, we have 2s and 2s above it, and these also combines to form our sigma 2s and sigma star 2s. Now for helium, we have 4 electrons, 1, 2, 3, 4. So 1, 2, 3, 4. This results in bond order equal to 0. We have already seen in the previous video. So when it gets excited, this 1 electron goes to the next orbital. So what happens in this situation? Then in the bonding orbitals there is 3 electrons, and in antibonding there is 1 electron. So the bond order comes to be as 1.0, as a result of which we can say that there is a bond. Similarly, the formation of He2 plus is also favored. We have already seen, as an electron from the antibonding molecular orbital is lost. Thus, bond order becomes 0.5. We have already observed. Thus, there will be existence of a weak bond between 2 helium centers in case of He2 plus, and in case of He2 star, what do we see? We see that here the bond order becomes 1. So, there is a stabilizing effect caused by excitement of electron, right? Now, we will deal with a important factor. We had already dealt with oxygen and fluorine molecular energy level diagram. Here we are going to deal with molecular energy level diagram for the orbitals of lithium to nitrogen. Here we will deal with a brief description of this using a correlation diagram, and in the next class we will deal with the molecular energy level diagrams. Now let us start. So first, according to the energy, we know that we have first sigma 2s, next comes sigma star 2s, next comes sigma 2px, next comes our pi for 2px and 2py. This will be 2pz, okay. Next comes our again pi x y for 2px and 2py, and last is sigma star 2pz. Now if you consider in this case, these will be applicable for fluorine and oxygen, but whenever we see about different elements like lithium to nitrogen, we have seen that there is a problematic representation, that is, there is an overlap between 2s and 2p. As a result, there is some kind of interaction which results in lowering of the energy and reversing of the energy. What happens is that if you consider this one, this sigma 2s becomes much lowered in energy. There is a strong bonding in sigma 2s as well as 2pz. This 2s and 2pz gets combined. As a result, sigma 2s becomes lowered and the sigma 2pz becomes higher than pi. So this is our sigma 2s 2pz. There is an interaction, but this is very weakly bonding. Now what happens? This sigma 2pz star will also go up, because this will also combine with 2s, and we will get this much above, higher in energy. Sigma, another left is this one. If you consider, this will also be lowered down, and we will have sigma star 2s 2pz. This is weakly antibonding. So we see here 4 features. One is this one, strongly antibonding. Next one is weakly bonding. This is weakly antibonding, and this is strongly bonding. These type of interaction where 2s and 2p are combining together to form different energy MOs, that is known as term interaction. And now we are now left with our pi. So this pi will remain as it is in this altitude. This is our pi, and pi star and pi will remain in the same. So as a result, if you can see here and focus, this part is getting exchanged, this particular part. Here previously sigma was coming first, but now pi is coming first, right? So in the next video we will deal with this MO picture. This one is very important to understand, otherwise it will be difficult for doing the MO energy level diagram. So let us see. Now according to the law of interaction, what we hear is that if molecular orbitals having similar symmetry are close in energy, then they will interact in such a way that one of the molecular orbital will be stabilized while the other will be energized in some extent. And we will deal with the diagrammatic representation of these interactions. If we first start with term interaction between 2s and sigma 2pz, we have this as sigma 2s positive positive, and sigma 2pz is like, here we have negative, here we have positive, and here we have negative, right? So this will combine further to give a big positive part, and here we will have a negative part, and here also another side a negative part, and this is known as sigma 2s 2pz, right? This is strongly bonding. Now what will happen? This will be combined in negative phase, out of phase, as a result of which what will happen is this one will change. This will be positive, this part will be negative, and this part will be positive, and this remains as it is. So we will get it like this. Here is our positive, here is our negative, and here is our again positive. So this is sigma 2s 2pz antibonding, that is star. So we can say that this is weakly bonding. Bonding because here the combination is being done to obtain a bonding orbital. So this is weakly bonding, and this is strongly bonding. Though it is combining in different phase, but there is combination occurring between the bonding orbitals. So this is bonding in nature, remember this. Now we will see the bonding interaction between the sigma star orbitals, sigma star 2s and sigma star 2pz. So if you consider for this, we have again like this. This is all antibonding. As a result, antibonding molecular orbitals will be generated by their combination. Positive, this will be negative, this will be positive. So on this combination we get it as, this is our negative part, this is our positive part, this is our negative part, and this is our positive part. So this is our strongly antibonding orbital, strongly anti-bonding. Now if we try weakly antibonding molecular orbital, so how does it look like? Same thing, but we will consider out of phase. This will combine like this, positive, and here we will have positive, negative, and this will be positive, and this one will be more negative. So this will combine finally to give here positive small, negative big. Here we have node plane, positive, and this is negative. So this is our sigma star 2s 2pz, and this is weakly anti-bonding. So if we want to summarize what is happening, see here. First, there is combination of the bonding molecular orbitals, and these bonding molecular orbitals is actually combining to produce what is known as our two bonding molecular orbital interactions, that is term interaction. In this case, the orbital which is formed in the first case is actually our bonding, strongly bonding. Next case, it is weakly bonding. And the other cases where antibonding molecular orbitals are combining, one gets strongly antibonded and the next one gets weakly antibonded. So this much for today. In the next video, we will deal with the different kinds of molecular orbital level diagrams for the lithium to nitrogen. So this was helpful. If you have any doubts, you can ask in the comment section. Thank you for watching. Don't forget to like, share, subscribe and comment.